All right, wrapping up our last Module 6 video, we will be talking about how you can set up and interpret the results of a paired samples t-test in SPSS. So for this example, we are going to be looking at a research scenario in which the purpose is identified that a researcher wants to test a new formula for a sports drink that improves running performance. From this question, the researcher collected 20 participants. Each performed 2 trials in a random order in which they had to run as far as possible in 2 hours on a treadmill. So the key word here is that they each performed 2 trials. That's going to be your indicator that you have a within subject effect or within subject independent variable. So we have repeated measures. Trial 1, they drank a carbohydrate drink only, and then trial 2, they drank a carbohydrate plus protein drink only. And then the distance that they ran in both trials was recorded. So from that, when we go into SPSS, again, we would copy and paste our data, make sure we're all set up. It should be that you have 2 columns of data that are both set as ratio. But I think students sometimes get confused because in an independent t-test, you're going to have a column of nominal data and then a column of ratio data. So the nominal data has the data labels that are identifying each subject with a particular group, and then the ratio values are going to be the actual measured scores. Now, when we have a paired t-test, or where we have repeated measures, we should have 2 sets of scores for each subject. And you'll recall that the rows in our data view represent a subject. So there should be 2 values per row representing 2 measurements per subject. One would represent trial 1, the next would represent trial 2, or we could also refer to it as a carb only versus a carb and protein. So once we have our data in to SPSS, the next thing we would want to do for paired t-tests is to check our assumptions. Now these assumptions we have to check outside of the normal output because they're not automatically included. And the assumption for a paired t-test that we said we have to check for, aside from all of our study design variable information, is that we have to have normality and no significant outliers of the difference scores. So these are going to be the same slides that I gave you guys in the lecture video where we went over the fundamentals of t-tests. So we're going to do the transform and compute variable pathway. That will then allow us to identify a target variable, which we will just call difference. And then in our numeric expression, we're going to say that our experimental group is subtracted, or our experimental group minus our control group represents the expression. So in this case, we're saying that because the major difference between carb and protein drinks is the fact that we haven't added protein, we're kind of treating the carb group as our control group and then the carb and protein group as the experimental group. Thus, the reason they are ordered the way they are in this slide. From here, once you go ahead and run that compute variable analysis, the difference scores should be added to your data view next to each of our measurements for the subjects. And now we can run an explore analysis on these difference scores to determine if we have a normal distribution of the difference scores, as well as if we have any outliers in the distribution. And the reason we need to check for this assumption is because this is kind of a way that we can see if our participants are actually repeated measures or not. When we have independent samples, the way that we kind of look at the variability in measurements is homogeneity of variance. So this is somewhat of a similar way that we can test that concept, but just when we have the same person measured twice. So you guys all know how to run an explore analysis, but just as a quick review, we would go to Analyze, Descriptive Statistics, and then Explore. You'll insert the difference variable into the dependent list. And then we're going to choose the Plots button to generate our normality plots with tests. So this should be the only box that's checked. And I made an executive call. We've talked about a lot of different ways that you can check for normality, but just so everybody's doing the same procedures so that everyone's answers match the key, so that way I don't have to make a bunch of keys. We're going to test normality using the Shapiro-Wilk test, and then we'll use the box plots to check for outliers. So once you have your normality plots and your tests all checked up, you can click Continue, and then we'll click OK back in the Explore dialog box. When you get to your output, you'll have some box plots, and there are a couple of different ways that SPSS will identify outliers. We want to make sure that we have no significant outliers, which we've continually defined as greater than 3 standard deviations from the mean, or 3 times the box length. So in this case, a circle, if there's a circle next to a case number, remember that case number is representative of the subject in your data view. So that case number corresponds to a value that actually is the outlier. That case number is not the outlier itself, right? But if we have an outlier that's marked with a circle next to it, that means it's an outlier that exceeds 1.5 times the interquartile range. For our analysis, these would be an acceptable outlier. We wouldn't need to get rid of them because the paired samples t-test is robust enough that these kinds of outliers won't actually affect the results that bad. If we have an outlier with an asterisk, however, that is indicating we have an extreme outlier that's greater than 3 times the interquartile range, or 3 times greater than the box length that we've identified for the rest of our sample. In this case, that would not be an acceptable outlier for analysis, and we would need to re-examine our data set and then consider if we should remove that particular subject. Maybe we measured something wrong, recorded something wrong, there could have been faulty equipment, we don't know, but it's kind of more ethical to remove them than to include them and have them skew the results of our test. From there, we've identified if we have any outliers or not. We can then look at our Shapiro-Wilk test to see if we have a normal distribution of our difference scores. So you can see the variable difference is here, and then we have the p-value for the Shapiro-Wilk statistic, which shows or can be interpreted based on the null hypothesis of that the sample distribution is normally distributed. Right? So if we end up with a p-value such as our example, 0.780, which is greater than 0.05, we would accept the null hypothesis, and our interpretation of that p-value would mean that the sample distribution of the difference scores is normally distributed, therefore our assumption has been met. In terms of the outliers, the first plot that I showed you guys in the previous slide with the blue circle, that is actually the result of this data set. So in this case, our normality and our outliers of our difference scores, we have met those assumptions. So once we have our assumptions checked, our next goal is to set up the analysis for the paired t-test, which is pretty similar to how we got to the independent samples t-test. So we'll go to Analyze, Compare Means, and then Paired Samples t-test. Thank you, SPSS, for making this simple. From there, you'll identify the variables that will be compared to each other. So these will go into a box listed as paired variables. And it doesn't, at first, you can insert your variables in any order. However, for this class, because we usually want to look at the comparison or the order of which we look at the difference of our variables, sometimes makes things easier. I don't know. The case in point is you can put them in whatever order you want to. For this layered statistics setup, they recommend that you input your variables such that variable 1 is your experimental group and variable 2 is your control group. The way that these are inserted now is not the correct order based on how this particular website wanted to set up the test. So if you ever end up in this situation, all you have to do is press this swap icon and it will switch the pairs that you've inserted such that variable 1 reflects the experimental group and variable 2 is the control group. Now there's some cases where there may not be a control group, in which case, again, the order doesn't really matter. It's just sometimes helpful when you're interpreting like the mean difference or the magnitude of the mean difference, that is. From there you can click continue, which will take you back to the paired samples t-test dialog box, and then OK to generate the output. So once we generate the output for our test, we can then interpret our t-test results. You'll get a single table, glorious single table. Well, you also have descriptive statistics, but this is the table that's going to be identifying your main effect. We can see our mean difference and our standard deviation, or the standard deviation of the difference. I think I showed, yeah, I did. In the first lecture video, I showed you that these two values actually can be used to calculate your effect size, which we will make sure you have practice with in the activity. We also have the standard error of the mean. Also, this is for the difference. And then we have our confidence interval, which is showing us what the true mean difference between carb and protein drink should be in the population. Now, it's important that you note what the order is of your variables, because the mean difference will reflect the actual numerical difference that was calculated. So in this case, we see carb protein minus carb. That means the carb protein mean minus the carb mean is how the mean difference was calculated. So you can usually tell which mean was greater than the other based on the order that they're inserted. In this case, carb protein mean was larger by 0.13550 as compared to the carb only drink. Okay. So that's just a little tidbit of information. We also get the t-statistic and the degrees of freedom. So you'll recall we had a sample size of 20. Degrees of freedom for a paired t-test, we subtract 1 because we have one sample, which is how we get 19. And then our sig column is going to be where our p-value is. So from here, again, remember we can never list a p-value as equal to 0 because there's always some infinitesimally small degree of error. So we would write this as p is less than 0.001, which is less than our alpha of 0.05, so we know we should reject the null hypothesis. And then recall the null hypothesis for a paired t-test is similar to the independent t-test, where we're looking to see if there's significant differences between our groups. So this is an example of how I chose to write the null hypothesis, just to give you guys more examples of how you can write things. And our interpretation, since our p-value was less than 0.05, would mean that there is a significant difference in mean running performance between the carb drink and the carb and protein drink interventions. Alright, that concludes all of our lecture videos for this week. Go ahead and watch those activity videos, give this some practice, and email me if you have any questions.